All right, here, so we're going to do some more covalent structures, but these ones could be single, double, or triple bonds. Phosphorus trifluoride. Phosphorus is a P. Trifluoride, 3 Fs. Figure out the central atom. Phosphorus is in group 15, so it has 5 with 3 gaps. Fluorine is group 17, so it has 7 valence electrons and 1 gap. Phosphorus is also the least electronegative, so that is our central atom. 1, 2, 3, 4, 5. There's 3 phosphorus, so I'm going to put them around the areas that have gaps already so I don't have to redo anything. And phosphorus is going to take up 1 gap and then fill in the other 6 valence electrons around. 1 gap, fill in the other 6 valence electrons around. 1 gap, other 6 electrons. Okay, and then we are going to check valence and octet. Okay, 6, 7, 1, 2, 3, 4, 5. So they both have their original valences. Octet, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody meets the octet rule. So I know that's good. So I'm going to rewrite it. And now I'm still going to remember to put those other 6 electrons around each fluorine, because otherwise it's saying that it's more like hydrogen. So make sure you're showing those extra electrons. And phosphorus has 2 that are unbonded, or 1 lone pair. So phosphorus trifluoride has this structure, and this is the process. Boron triiodide. Boron, group 13, 3 valence electrons. Iodide, group 17, 7 valence electrons. Least electronegativity, most gaps, but recognize that boron only has 3 gaps because there's no electron here to share with. So there's no fourth side to this boron, so you can only have 3. Boron triiodide. Boron goes in the center. I'm spreading around the 3 electrons because they can space themselves out so they can accept bonds. I just can't magically put a 4th electron there for boron. Okay, and iodine is going to fill in the gap of sharing and 6 other electrons around. Fill in the gap of sharing, 6 other electrons around. Fill in the gap of sharing, 6 other electrons around. Boron has 2, 4, 6. He does not meet the octet. Boron has an incomplete octet, but he still matches his valence, so he's okay. Iodine has 7 valence electrons, so he matches his octet, and he has 2, 4, 6, 8. So he balances his, I don't know what I'm saying, he balances his valence with 7, and he balances his octet with 8. So when I rewrite this, I'm going to space this out a little bit more because all those atoms are going to go so they have the most space. So when I rewrite boron triiodide, I'm going to make him more like this I structure. Okay, again, still 2, 4, 6 for boron, 2, 4, 6, 8 for each iodine. Dihydrogen, so H2 sulfide. So at this point, I know that sulfur has the most gaps. 1, 2, 3, 4, 5, 6. So I can just say central, 2 gaps, instead of redoing those dots each time. Okay. Hydrogen has only 1 electron, so he's just going to fill in each of the little gaps. So when I rewrite him, he looks a lot like the Mickey Mouse molecule. Well, that makes sense because hydrogen is on the ends of water and oxygen is in the same group as sulfur. So it makes sense that they would have a similar bonding because they have a similar structure. 2, 4, 6, 8 meets valence. 1, 2, 3, 4, 5, 6 meets octet. Because remember, you can pretend like these are little barbells here, so you can see there's 1 electron from sulfur and 1 electron for hydrogen. They're holding hands to make that single bond. And hydrogen, of course, is full with 2 electrons because he only has a quantum level of 1. Oxygen gas. Okay, well, there's no central here, so they're just going to be 2 oxygens. And I'm going to start with a single bond. So I'm going to pair these guys up because they're right next to each other, so that makes it easy. And now I'm going to check valence and octet. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I didn't add any electrons. Sometimes people magically add electrons, like the boron triiodine, to make that octet. You can't magically add electrons. Conservation of mass. And now octet. 1, 2, 3, 4, 5, 6, 7, because he has his original 6 and he's sharing 1, 7. Well, he's not happy there. We need to have 8. Okay, and the same thing would happen if I checked on this side. 1, 2, 3, 4, 5, 6, and sharing 1 for 7. Definitely did not meet that octet. So I'm going to draw a second bond around. So this oxygen has 2 electrons that he's sharing to the other oxygen who has 2 electrons. So I have 4 electrons shared here, which is equal to a double bond. And again, this is the process part, so make sure you're showing these little ovals so you can confirm, prove your hypothesis of what it looks like. And now, 1, 2, 3, 4, 5, 6. I have 6 original plus 2 is 8. 2, 4, 6, 8. I now meet the octet. So I can redraw. And now I just draw those ovals as lines. 2 electrons, 2 electrons for a double bond. Okay, this guy up here is not a double bond. That is hydrogen single bonds with sulfur and another hydrogen single bonds with sulfur. But this is going between the same 2 atoms. What else do I have to do? Write down what else I have. I have 1, 2, 3, 4 electrons that are unbonded. So I'm going to write them on the other side. Always remember to go back and check. Do I still have the right number of valence? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes, I still have the right valence. I didn't forget any in the transition. Okay, that's a big mistake people make. Go back and double check your valence and octets. 2, 4, 6, 8. 2, 4, 6, 8. All right, so I'm still matching my valence and octets, so I know this is what oxygen gas looks like. Notice I had to know oxygen gas, Brinkelhoff, to get this question right. Carbon dioxide. Carbon, I know, has 4 gaps. Oxygen has 2 gaps. Formula is CO2. So I know that carbon's going to be my central ion. So that's all I need to show now for proof that I know I selected that central ion. So don't forget about that step. 2, 3, 4. I'll put the oxygens on either side. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Always start with a single bond because otherwise it's not a chemical structure. So every atom has to be single bonded to somebody. So I did oxygen to the center and the other oxygen to the center. 2, 4, 6, right valence, plus 1, 7. All right, so I'm thinking this is going to happen exactly like oxide is. So I'm going to grab a second 2. And remember, you can grab any 2 that you want. It doesn't matter. Okay, just as long as you have an electron from the center and an electron from the outer. Electron from the center, electron from the outer. Let's check out our valence and octet. 1, 2, 3, 4, 5, 6, sharing 2 from carbon, 8. Okay, so that oxygen's good. How about the carbon in the center? 1, 2, 3, 4 to start with, so he can only have 4 bonds because he had 4 gaps. 2, 4, 6, 8, so he meets valence and octet. 2, 4, 6, 7, 8. Okay, so we now meet valence and octet, so we have proven the process. So let's rewrite. 2 ovals connect, that's C and O. 2 ovals connect the other C and O. What's left over? 1, 2, 3, 4. 1, 2, 3, 4. Hey, that's a pattern. Oxygen seems to oftentimes have 2 extra pairs of electrons. These aren't lone pairs. Lone pairs are always around the center. So this is an oxygen double bonded with carbon, and another oxygen double bonded with carbon. It is not a quadruple bond, and there are no lone pairs because there's no extra pairs around carbon. We do have unbonded electrons because they're not connecting to anything. Okay, and so that's that structure. Okay, P2. Okay, well, no central atom, so I'm just going to go right to drawing around 5 valence electrons because of group 15. 1 layer, check valence and octet. 1, 2, 3, 4, 5, 6. Nope, not there yet. Second bond, 1, 2, 3, 4, 5, 6, 7. Not there yet. 1, 2, 3, 4, 5, 6, 7, 8, or 2, 4, 6, 8. Meets valence and octet with a 1, 2, 3 bond order of 3, or a triple bond with 2 left over. See how I try to write it kind of like it's symmetric. So when you can, rewrite it so it's kind of symmetric. S2. Okay, no central atom. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Single bond. 2, 4, 6, 7. Not happy. I'm just going to go right again and draw that second one. Now let's check. 2, 4, 6, 2, 4, 6. I did not magically create any electrons. 2, 4. So a double bond because there's 4 electrons shared. 6, 8 for the octet. 2 bonded pairs, 2 unbonded pairs. 2, 4, 6, 8. So we meet the octet. Process. Make sure you're always drawing the process. And again, sulfur looks a lot like oxygen because they're in the same group. Methane is carbon tetrahydride. Carbon has 4 gaps, so they can do 4 bonds. Hydrogen has 1 gap, or 1 bond, so the central atom is going to be the carbon. And there's 4 hydrogens, because tetra means 4. So I'm going to spread that around. Each hydrogen has an electron bonded with each of the carbons. Okay, 2, 4, 6, 8. 1, 2, 3, 4. 1, 2, 3, 4. 2, 2, 2, 2. Always check because you can get mixed up when you're putting the things down. Carbon disulfide, that's my central because he has 4. Sulfur just has 2. CS2. Carbon goes in the center. 2, 3, 4. Sulfur 1, 2, 3, 4, 5, 6. Sulfur 1, 2, 3, 4, 5, 6. Single bonds between the outer and the center. 2, 4, 5, 6, 7. Okay, I'm just going to go to a double right there. And since these are the same guy on both sides, I know the other side needs a double. 2, 4, 6, 8. 2, 4, 6, 8. Okay. Did I magically add any electrons? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, so valence checks out, octet checks out. Physically write that down so you don't forget on the test to check that. C has 2 ovals, or a double bond, with 2 pairs of leftover electrons, unbonded electrons. And that happens on both sides. A fairly symmetric molecule. C2H2F2. Well, 4 gaps, 1 gap, 1 gap. So carbon's going to have to be my central atom. And I have 4 guys going around it. Now, for you, you're just going to magically put the 4 however you want to put around it. 2, 3, 4. Carbon has 4 bonds. Hydrogen has only 1. Fluorine, remember, don't forget and just give him 1. You have to show him different. Rewrite. Don't forget the extra electrons. 1, 2, 3, 4, 2, 4, 6, 8. 1, 1, 2, 2. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 2, 4, 6, 8. 2, 4, 6, 8. Okay, we have our valence and our octet. If you're still confused on how to count valence and octet, go back to the videos and watch that carefully to make sure you're getting that right.